This is a conversation with Ben Raana, who is a software engineer at the Monterey Bay Aquarium Research Institute, or MBARI for short. MBARI uses robots to monitor and explore the oceans to better understand climate change and other topics. In general, getting ocean data is extremely expensive. Depending on how far the area of interest is from the shore, it may require a large boat with a full crew. MBARI is working to make this process easier and much cheaper by having robots stay at sea for weeks at a time getting data on different ocean events. This generates a lot more data and will hopefully greatly improve our understanding of our oceans. I found it exciting to talk with Ben about how MBARI is looking into having robots stay at sea almost indefinitely, charging their batteries and uploading their data all while at sea. This could enable fleets of robots to continuously be at sea, giving us a much richer picture of the health of our oceans. I'm Audrow Nash. This is the Sense Think Act podcast. Thank you to our founding sponsor, Open Robotics. And now, here's my conversation with Ben Raana. Hi, Ben. Would you introduce yourself?
Sure. Hi, my name is Ben Raana. I'm a oceanographer and robotics software engineers here at the Monterey Bay Aquarium Research Institute, or MBARI for short. We're in Moss Landing, California. I've been here with the Institute for probably coming on 8 years now, working as an engineer. A bit about my background. I actually started my ocean career about 20 years ago. I was a special warfare operator and a combat diver in the Israeli Navy, and spent a good chunk of time with the teams there. And later on got my undergrad in marine science and biotechnology back home in Israel, and then came here to get my master's in physical oceanography. At that point, I got involved here with the Institute through an internship, and then I just refused to leave. So here I am. So now mostly what I do is I work, do development and operations with autonomous underwater vehicles. And I also have a few projects running that I think you're interested in, and I'm looking forward to talking about.
Awesome. So what kinds of projects do you guys do at MBARI?
Yeah, so I guess maybe before we dive into the projects, I can tell you a little more about MBARI in general. I think
Sure.
You may be familiar, but others may not. So like I said, we're in Moss Landing, California, that's Central California. I'd say probably about an hour south from San Jose on the coastline in the Monterey Bay. And MBARI is actually a pretty unique ocean research institute in the sense where we're a private nonprofit. The institute is not an academic institute. It's kind of been founded as an alternative to what an academic institute can be for ocean research. MBARI is funded almost exclusively through the David and Lucille Packard Foundation. And David Packard, which is the P in HP and Hewlett Packard, he founded this, he founded this institute in 1987, so we just celebrated our 35th birthday. And the mission back then was to, like I said, offer an alternative to traditional academic research institutes and take on challenges that require development of technology in order to, answer some of the scientific questions that marine scientists may have. And so that's kind of been the goal of the Institute, and also remove a lot of the, barriers, especially when it comes to funding. And so scientists and engineers here get to focus more on the doing and less on the proposing. And so we have an internal proposal cycle in which we, form a budget, and then we get funded through the Packard Foundation, which is phenomenal. It's absolutely great. And so the way the institute is structured is we're actually kind of like a three-legged stool, or a trifecta. Never skip on an opportunity to say that word. And so, yeah. So the institute has about 220 employees. We are divided into science, engineering, and marine operations. And we work very closely together So the barrier or the boundaries between the groups is very blurred. You know, you got a lot of scientists that are very much engineers and engineers that are scientists, and they work together to find the questions that need to be answered, and then develop the technology that allows us to go out and get that. And then the Department of Marine Operations has the specialty and the knowledge on how to deploy the assets and manage, and also, make sure everything comes back safely to the best of their ability. And so that together is what I think really makes the Institute special, and its ability to come up with very challenging questions, develop the technology to try and gather the information that's required in order to answer those questions, and then actually go in the field, gather the data, and start working on the answers. And so that's kind of like a cycle that we exercise here pretty regularly, and it's all good fun. Yeah. So I guess that's the institute. That's the institute in a nutshell.
And what kind of problems are you guys typically? So in Hewlett Packard, so Packard set this foundation or set this up. So he sends you guys a good amount of money to do the research. What kinds of problems are you guys most interested in solving, or like what kind of problems are you going after, I guess?
Yeah. So if you walk around the halls here, you'll find scientists pretty much of any ocean research discipline that you can imagine. So we have geologists, geophysicists, chemical oceanographers, biological oceanographers, any kind of type of marine research really that you can imagine is happening here. And so at the core, we're trying to describe the oceanic environment and go after questions that also have to do with anthropogenic impact that's driving change in the ocean environment.
What does that mean?
So
anthropogenic, is that
is human generated? So that really relates to some of the challenges that we're faced with climate change and how emissions, for example, impact our environment. And so the ocean is actually a really important piece in buffering the heat on the planet. And so in order to understand better the processes that govern heat transfer, how carbon dioxide that gets emitted into the atmosphere gets absorbed and back in the ocean and buried in the ground. That's the carbon cycle. So the Institute is trying to target research in order to acquire data and figure out what governs these processes, what are the rates, and then through this research inform larger models that have to do with climate change and more of a global scale, in the global scale sense. So those kind of questions, they really drive research in all the layers of the ocean. So from the atmospheric to the upper water column, where the gases kind of mix, and then how the biology interacts with the different chemical properties of the water, different physical properties of the water. They take in some of this carbon and use it to build their bodies, right, through photosynthesis. And that later on feeds the large organisms and cascades through the food web. And eventually, those kind of fixed organic compounds are either pooped out or die and sink to the bottom of the ocean, right, and get buried there. And so that is the carbon cycle in a nutshell. And we focus on research that tries to describe each of those sections in detail. And then,
Gotcha. So you have, just to see if I understand the carbon cycle, you have carbon in the environment, then you have small like algae or something, some small things that will consume the carbon and sunlight and this kind of thing, and the photosynthesis happens, then they go through this whole process where they're eaten by fish or something, and somehow they like eaten by one fish that's small, a bigger fish eats that, whatever. Eventually something dies in there, and then it sinks to the bottom of the ocean. And what happens when it's at the bottom of the ocean? It kind of just stays there for a while, and you get kind of like
Well,
this soot on the bottom of the ocean, or
yeah, so it gets embedded as sediment, and the ocean seafloor really is, I guess, the storage of that carbon until either it gets. Then you're starting to look at geological processes on what happens there, how yeah. So how does the ocean seafloor evolve over time, and when does that carbon make it back into the atmosphere? And so I guess the point is, yeah, so we've described a lot, and I guess the point to really kind of take away from this is that these are processes that happen over many, many, many timescales and over very different, over very different spatial scales as well. And so at MBARI, we kind of talk about it in the sense of, going from molecules and atoms to ecosystems and back. And so the type of science that we do here goes from understanding the microbial processes that, what type of nutrients are required in the ocean in order to make these biological plankton or bacteria flourish and take in these gases. But then all the way up to how does it later cascade into the food web, and what are the timescales that are associated with those things. And so that on its own poses many challenges, because in order to collect relevant information to describe these processes, you really have to be at sea a lot and have to be there not only for the duration, but also in the right place, and cover and span the area that's required in order to really capture those phenomena.
So if I understand correctly, it sounds like you guys are basically trying to model, so the carbon cycle and what's occurring, to accurately model that and have a better idea for climate change, you need to be involved at something through the whole spectrum, which is a massive process that happens everywhere in the ocean, at all different times with all different creatures. There's lots of things involved. And so because of this, this makes it so you guys have a very large research mission, in a sense. Like, there's a lot of things that you need to understand, or there's a lot of monitoring that needs to happen, so that you can begin to refine your model, so you can have a good idea of this process and maybe its impacts or maybe its changes over time and these kinds of things.
Exactly. And the idea is that eventually this type of information can cascade into decision makers for conservation management, and other type of decisions that impact our environment, but also can impact some of the livelihood, for example, fishermen, and so on.
So that sounds incredibly lofty, as in a huge, huge challenge to basically take on climate change. Is that motivating everything at MBARI, or are there other problems that you guys are interested in too? Like, clearly that's enormous. And is that everything under that umbrella, or are there other umbrellas?
Well, there are other themes as well. I mean, you have researchers here, for example, that are behavioral ecologists, and they're interested in describing.
I don't even know what that means at all.
Well, they're interested in describing, how certain species behave underwater, and so
that's super interesting.
Right. So you can imagine, for example, if you're interested in studying squids, especially if you're interested in studying deep sea squids. Then again, getting access to the environment where those squids are is an enormous challenge, and one that's very suited for an institute that is capable of developing the technologies and also executing the operations. for getting the right information. And so, that's another type of research that we do here. We also have a whole mapping division. We use vehicles to go in and do surveys of the ocean seafloor and map the ocean seafloor, and then return to see how it evolves over time. So that's a whole kind of branch of geology that we host here. So really, it's very hard to try to capture all the activities that go on here in the Institute. I'd say climate change has definitely been one of the main themes, and the impacts of climate change on the ocean environment has been one of the main themes that have governed a lot of the proposals and the projects that happen here. But it's not the only one. There are other projects that maybe don't fall exactly under that umbrella, but that is definitely the lead theme.
Gotcha. And largely ocean related. I mean, well, entirely ocean related, it sounds. And then it's also, I mean, if you have better ideas of how these creatures behave, maybe you have a better idea of how they are as actors in the system, which helps you model these things. And if you have better maps of the environment, perhaps that also helps you in environmental monitoring, I could imagine.
Right.
Which all go back into climate change in some sense, because it's such a large problem that having an accurate model has so many pieces too.
Correct. And then I guess I'll add that MBARI has been a major player, since the 80s, collecting this type of information. And so at this point, we've gathered enormous quantities of data, and we are working pretty hard to make this data available for others to use, and also process it here and have that multi-decadal perspective in order to quantify change in the environment. So in other words,
really cool.
We're establishing a baseline starting from some point and looking and observing how the environment changes over time. And so another big mission of MBARI is to safeguard this trove of data and make it accessible. And so I think that's another thing that the Institute is unique in its capacity to offer. So
that's really cool. Now, so that's awesome. What are some of the ways that you guys have been using robots in these different parts of kind of the mission of MBARI?
Right. So, we refer to oceanography here as a contact sport. Like I mentioned, in order to gather the data, you have to be in the environment. And so, as you know, traditionally, oceanography for decades has been done using ships. And that's great. I think that ships and humans are always going to be part of this type of research. And MBARI indeed operates two large ships that go out and collect data and take expeditions at the sea. But I think there's also a realization that, because of these temporal and spatial scales in which the phenomena that we're interested in studying happen, we're just not able to be there all the time.
It's hard to get humans to be everywhere all at once, for sure. So it's much easier to have robots go do it, for sure.
It's not impossible, but it is cost prohibitive.
Yes, for sure.
So
and also, then there's human error and all sorts of other things, too.
Sure. I mean, robots make mistakes also, especially people that operate them. So, and in fact, because, traditionally, this type of research has been done using ships, and MBARI has also put a lot of resources into calibrating the measurements. Okay, so you've done and collected data in a certain way for a certain number of years, and now you're switching into a more automated collection system. And so how does that data compare, and what are the calibration factors that you need to apply to go from manually collected systems into using data that's collected by automated systems? And so that's
so making sure that we have consistency from humans taking it to, maybe if you can automate it and have a robot do it, you want them to be apples to apples, not apples to oranges. So you have this big break where the data is like completely different and thus hard to draw conclusions from.
Exactly. So you don't suddenly think that there's, some kind of climate crisis that happens to coincide with the time you started using certain robots.
Gotcha.
So We've been seeing through this transition now. Some of the environments that we research are very hard to get to. So, for example, kind of the average ocean depth here in the Pacific is about 4.5 kilometers.
So just to put that, 4.5 kilometers, that's 45 football fields deep, roughly, or
roughly so, yeah. And
if
you think about,
yeah, sorry.
Yeah, so that's very deep. And when you think about, for example, the type of pressure environment that we live in, we live at 1 atmosphere of pressure. If you go to space, you're almost at 0. But if you go about 30 feet down underwater, then you've already doubled the pressure. And every 30 feet you add a whole other atmosphere. So those...
How many atmospheres are down there then?
We'll have to do the math. So
you said 4.5 kilometers down?
Correct. It's 1 atmosphere per 10 meters. So if you have 4,500 meters, then you'd be at...
Divided by 30 feet per, or 10 meters is 1 atmospheric?
Correct. Yeah. So 450 atmospheres, I believe, is the number.
Oh, yeah, that's an easy one. Okay, yeah. Doing math quickly doesn't always work. But
especially not on while you're being recorded.
Not while for sure. So 450 atmospheres.
Correct. So I guess the pressure is immense, and so in order to take humans into those kind of environments and support human life in those environments, it comes with a huge overhead, and it's not risk-free. And there are systems that do that. We have deep sea subs. Woods Hole Oceanographic, I believe, operates Alvin, which is a human submarine that's able to go to those kind of depths and collect information there.
That's wild.
But it's not really scalable. And
did you say average depth is that much?
Correct.
What's the deepest? Like, well, I guess we probably don't have a very clear idea, but what's...
Oh, we do.
Okay.
Yeah. So
how far down does it go?
It's over 11 kilometers.
Wow.
That's taller than the tallest mountain, right? That's
so 1,100 atmospheres.
Correct, and I believe that's the Mariana Trench off the coast of Japan, which is that's pretty deep. But humans have reached there, and vehicles have gone down there as well, and so it's not out of their reach. It's just not very scalable, right? I guess is the point. And like I mentioned, again, a lot of the phenomena that we're also interested in studying are very patchy and episodic in nature, meaning, you can imagine the wind blows a certain direction, the currents do a certain thing, the nutrients emerge, and then suddenly, boom, that creates an opportunity for something to occur. And you're either there or you're not. And sometimes you can be... I'm sorry.
Can you give me an example? Like, what might an event that you're trying to see occur be? Like an algae bloom of some sort, or
that'd be a classic example. So typically, the way this occurs is winds blow, they push coastal waters away from shore and pull in deeper waters that are much richer in nutrients, and that allows for this community of microorganisms, plankton, and phytoplankton to really flourish. And that mostly happens on the upper part of the ocean where there's access to sunlight. And so when those conditions come together and those blooms occur, you're either there to catch it or you're not. And you either have a platform that's able to go out and collect this information or you don't. And so I guess once that window of opportunity closes, and typically that's on the order of weeks, spanning I'd say tens of kilometers, at least in the coastal environment, then your window of opportunity is gone, and you've lost your chance to collect the relevant data. And so having autonomous platforms that are able to persistently be in the ocean and collect information is a huge advantage. And so kind of segued away from the deep ocean back, to the upper water column, and we operate automated systems in both. But you either need a very a system that's capable of operating in those depths, or you need a system that can operate up in the upper water column that's capable of having that persistence and endurance to cover those areas. And so in both cases, those type of problems lend themselves very well for automation and for use of autonomous platforms. And so MBARI has developed, at the beginning, we were very focused on getting to those depths. And so MBARI was one of the pioneers in developing remotely operated vehicles. Those are big, kind of cube-like vehicles that remotely operated vehicles, ROVs.
Oh, okay. Gotcha.
And so those are tethered vehicles, and they're piloted remotely from a ship. So those still require a ship to be in the area, and then
and a very long cable.
Correct. Yeah.
Going from the robot to the ship. Yeah.
Yeah. Correct. And so MBARI has been invested heavily in developing those type of technologies, and also coming up with ways to manipulate, the environment there with robotic arms and so on and so forth. And then more recently, we focused on using autonomous vehicles to extend the duration. So cutting the tether, focusing on platforms that can sustain themselves in the environment with a remote operator that only supervises periodically. And that really gives you ability to design without counting on having a ship in the area. And B, it also opens the window for scalability, right? So
because you don't need the big staff to maintain them and be running. Like, you don't need a whole ship going to the one location, because you just have a bunch of these making their way around the ocean, monitoring things.
Correct. And you can also have an operator that, rather than being fully engaged in operating a machine, is now checking in periodically just to make sure things are happening as they should, and maybe providing instructions for correction. And so
the grocery store checkout model is everywhere these days for this kind of thing, where you have like the one person watching the 10 machines. It's so interesting to see it here too, where you have one person kind of supervising, but not paying attention all the time to all of the robots in your groups, but just watching a few that periodically come in and out of contact, and they manage maybe giving high-level directions or something like this. It's so interesting. This is becoming everywhere, it seems.
Yeah, and I guess there are some aspects of doing marine robotics that I guess are very different from terrestrial robots or aerial robots in a sense. So I think the underwater environment is a communication denied environment, meaning once you go under the radio frequencies that we use for localization, then radioing between our vehicles diminishes at that point. Where our only option to communicate with the vehicles is acoustically using sound underwater. And that presents a whole another set of challenges. And that technology's come a long way, but it's still very limited, especially compared to
way lower bandwidth, I would imagine.
Correct. Like, so you're talking about
far less information can be sent.
Right, bits per second, and then very limited in range. With typical range, I'd say a few kilometers is kind of typical.
That's crazy.
Yeah, so the vehicles really need to be self-sustained, and they need to know what to do and operate on their own. And so that's a challenge, but at the same time, as humans, we're not really able to be in that environment. It's hostile for our bodies. Any kind of system that you can put out there and can execute a task that's useful is going to be an improvement of what, on top of what a person can do. And I feel like here in terrestrial robotics, we're always up to a challenge, because, you gotta do as well as something that as well as a human, where you're already in an environment where humans can function fairly well. So, so we have many challenges on one hand, but then, in some ways, it's kind of easier to make fast progress and push the needle further than what you would be able to do in environments where humans are, capable.
Yeah, because it's so I'm a little confused, but so you're saying because these environments are so challenging to get people out there, and there's budget restrictions and things, because like you can't have a ship go to each location you need or you're interested, but you can have a robot that kind of manages itself much more cheaply. And so because it's so hostile and because of the scalability problem, there's a lot of room for advancement with these robots that are going at the kind of the shallow depths and monitoring things autonomously. Correct? Or
no, yeah. I mean, there's just pretty much any kind of if you can get a system to execute any kind of task out there at sea, you're already pushing the needle forward. You're improving over what a human can do, and so I guess that's one advantage of doing marine robotics. But it might be the only one, because it really is a very hard. It really is a very hard environment.
Oh yeah, totally. I imagine it's like almost, if not as difficult as like putting a robot in. Like if you put a robot in space, it's like tremendously difficult to get it up there. But once it's there and it's in a harsh environment, that's a big challenge for sure. Like putting a rover on the moon or putting a rover on Mars or putting something in space. Like that's tremendously challenging given the harshness of that environment and the remoteness of it. But this is kind of similar in that the environment's like water is really powerful. It's very cold. It's very rough. There's like, I don't know, a bunch of creatures all around. I don't know. I'm imagining sharks.
It's true.
And stuff.
We did have sharks attack our vehicles in the past, so vehicles have returned with shark bites in them and teeth embedded in the fairings. But
crazy.
That's actually a really good comparison. But I guess I would argue that because the pressure in space versus pressure at sea, we've already talked about that. So the vehicle, you need to be able to sustain those pressures, which is a challenge. But also, even a vehicle on Mars, sure, you have a 20-minute to 20-minute back delay in your communication, but you're still able to communicate with the vehicle at all times.
Yeah,
versus exactly. Versus an underwater platform where once the vehicle's under, you typically lose contact.
That's very interesting for that. It's definitely a very hard problem space. One thing just to give, because this is one thing that I don't quite understand yet. What kinds of things, because these robots are out there and they're monitoring something, but what kinds of data are they collecting while they're out there, like specifically? And I'm sure there's a lot of things you could look at, but like the nature of the type of data you're collecting is something I don't yet understand.
Sure, yeah. So we have platforms, different platforms are geared toward collecting different types of information. And so if you're looking at an ROV, that's a remotely operated vehicle, that has the option to manipulate. And so you can
like little hands.
Right, exactly.
Grab things. Okay.
And so you can do specimen collection, for example, at the deep sea. We also use those type of platforms to do surveys of the seafloor using video, multi-beam sonars, and also for mapping, and also now LiDAR. And
really, that works under, I mean, I guess it makes sense that it works underwater. I imagine there's a new set of problems and challenges with that.
Yes, it's very challenging. I'm actually not working on those projects, but we have a whole team here that's developing that capability, and it's pretty cool, actually.
So cool.
Yeah, so they've developed actually this really cool device. It's I can share a video later, but it's an articulating sled that connects to the remotely operated vehicle, and it allows the vehicle to conduct a survey. So you can imagine it flies over a constant altitude, but then regardless of how what the bathymetry does with the bottom of the ocean. So for example, now you're coming up against the wall, the sled will articulate itself. So the sensing is always pointed directly at the seafloor. And so that allows you to get continuous surveys regardless of what the topography is doing underwater. And with LiDAR, imagery, and sonar, you get very high resolution data. And so you can start describing species to the genus level using the imagery.
That's so cool.
And then by returning to those points, you're able to track how things evolve over time. And so that's something we do, and that's one type of information that we gather. And MBARI, those images and videos that we collect are one of the biggest, I guess, databases that we have is those videos that these vehicles collect. And we have also some projects going on here now to expose some of that information and make it, bring it to a format where is ripe for automation. And so that's one type of data. Then we have also autonomous vehicles that also carry, those are deep sea vehicles, so also geared towards mapping as a primary task. And they also carry these big sonars and are able to do these surveys along the sea bottom at depth and retrieve high resolution maps of certain areas. And so that's another type of data that we collect. And then in addition to that, we also have what we refer to as oceanographic sensors. So most typically, those are going to be sensors that collect temperature, salinity,
And that's how salty it is, right?
Correct.
The second one, salinity.
Salinity, correct. And the way, yeah, so that's kind of like your basic, but then you have also specialized sensors that are able to tell you the concentration of certain nutrients in the ocean water, for example, like nitrates sensors, things like that. And then we also have even more specialized sensors that are able, for example, to sense the type of bioluminescence. So they have a chamber that pass, so you can see how much bioluminescence occurring in the body of water that you're traveling through. And so that's another type of...
So does that mean like an algae will produce light at night or something? Is it an algae, or would it be like fish in the really deep ocean, or both, or...
Yeah, so bioluminescence is light-emitting organisms. And so that actually happens in a very wide range of species across the entire ocean. So it's pretty ubiquitous, and we have a lab here that studies how it happens and what are the evolution pathways that lead to different types of patterns.
That's really cool.
Yeah, so that's another type of,
Is it often in deep sea animals, or do you see it in like surface algae, or like, I don't know if like the ocean lights up at night with algae. I could imagine that, but I wonder if it's true.
No, it is true. So larger organisms that have bioluminescence are typically found deeper, and they use bioluminescence for various reasons. It could be for attracting a mate, for trying to capture prey, for deterring prey, and you see different patterns and different colors being used for different purposes. In the shallower water, there are many types of algae that have bioluminescence for different reasons. And we actually have a project going on here to try and identify what type of algae you're observing just based on the bioluminescence patterns. So yeah, so it's actually a pretty ubiquitous in the ocean. It happens in all kinds of...
Just out of curiosity, like, I don't really know anything about this, but why? So I can understand animals having bioluminescence because they are like, as the reasons you've mentioned, hunting or mating or something like this, like it's beneficial for those reasons. But plants, I can't, like, algae is a plant to me, and I can't understand like how that would affect, like if there's one algae and it has a beautiful glow, it doesn't probably help that algae mating with the other one, or maybe it's some reactive. What's the reason why algae has bioluminescent glows?
Well, I don't have a straight answer.
I'm sure there's many.
But... Yeah, there are probably a few. It could also be for predation avoidance, if they all fluoresce all at once.
I guess it looks like nuclear waste or something in some stuff. I don't know.
Well, if you try to imagine trying to capture one little particle, but suddenly a light show blows up in front of you, I think it would be pretty hard to focus on just on one single cell. But I'm not sure that's really the reason. We'll have to get
I
back
could
to you
see
on
that
one.
being some sort of thing. It's avoiding predators. I just intuitively, I don't have a good model for why that would be the case, and it's fascinating that that exists. But
Right.
okay.
Yeah. And so Steve Haddock, Dr. Steve Haddock here in MBARI, he leads research here on bioluminescence. And so we can go ahead and look up some of his research and probably get some answers. But he's great.
So you
I
have
guess,
those sensors. So you have bioluminescence sensors, and you mentioned a whole bunch of other ones. So salty and temperature and
nutrients.
the different nutrients.
Correct.
So those are the kinds of things you're collecting data about. And I guess also the video one. So if you see an algae bloom, what kinds of things are you trying to sense about that? I suppose the nutrients, how salty it is, the temperature, but then also maybe video of the event, and then
So for biological for studying those type of microscopic organisms, we do have some imagery-based payloads that we use in order to try and identify species.
So you mean like various cameras, camera setup or something that you include on the robot. So you have various payloads that have various sensors that you might include on your robots. Okay.
Correct. And in addition to that, we also have the ability to acquire water samples autonomously at sea. And so we have a whole lab here that's actually, that's their focus, and they've developed a payload called the Environmental Sample Processor. And this is actually probably the most advanced type of, it's not really a sensor, but it's more like a payload, we refer to it. It's able to take in 60 water samples. So you can imagine some kind of like a system that has an intake and is able to filter water while the vehicle is deployed at sea, and then also has some automation that's built into this payload to use the right reagents in order to fixate that sample so it doesn't continue to change after you've filtered the water. And then that system also has...
So that would be like if you had some sort of bacteria in it or something that would like continue to do whatever. So it like you'll basically sterilize everything or kill everything in it so you can look at its components, and then you can easily subtract that reagent out when you are doing your tests on it, so you know kind of your baseline and you can see what it was at the time.
That's exactly correct. And then these payloads also have some analytical modules that are able to tell you things about the sample that you just acquired at sea.
Cool.
And so at the extreme case, and this is still hasn't been miniaturized to the point where it runs on a vehicle, you can run this type of sample and actually target specific genes. So do almost like a genomic analysis on the sample that you just acquired and radio back to shore.
What are the genes of, is it literally genes of something? Are you like getting an algae sample and looking at its genes, or what is it it's okay, so it's an algae that you're synchronizing effectively. That's super cool.
Yeah, and then that allows you over time in space to see, what was the what was the community, the microbial community, what was it looking like, and over time, how has it evolved, and that is really useful for research and understanding how things change over time and with conditions. So as conditions change, how does the microbial community react? But also, it's very useful for monitoring. So you can for example, you can imagine seeing a system like this deployed somewhere and looking for a certain species of algae that's harmful for the environment because it produces some toxin, and that's kind of like an early warning system. So again, geared toward not only doing research but also conservation and resource management. So that's another piece there. And so that generally that payload kind of personifies, I guess, one of the major themes of research that have been going on here in the Institute, which what we refer to as taking the lab to sea. And being able to do sample processing and do as much of the analysis that we can at sea and inform the vehicle autonomously on how to proceed. And so taking the lab to the ocean, to the sea has been a major theme here. And the type of development is also, it's always geared to, if you could do it here at sea or on a ship, how can we take that same analysis and put it on a platform? And so this water sampling pit that I just described, for example, now we're at the point where we're adding these modules that are able to also analyze the samples and have the vehicle do this type of analysis at sea and radio the results back to shore.
Gotcha. Okay, so they radio the results back. So this is for like one of those surface monitoring robots. So it'll kind of like stay at some depth that's not very deep, collect some information, and then it goes and it chills at the very surface in the water, and it'll radio back the information for you guys to analyze. Correct. Or do something with. And probably that's how you communicate with it, for like send it commands or something as well. Right.
So the vehicles actually, they can also use some of the sensor input to inform their actions. We have planning algorithms, for example, that look at sensor input and decide how to steer the vehicle autonomously, for example, in order to try to stay with some kind of maximum concentration where you're sensing where most of the algae is, or where the highest concentration of algae is. And you can use optical sensors to try to see how much chlorophyll is in the water using fluorescence. And so then you can use this information and drive the vehicle to do kind of like you can imagine a gradient climbing algorithm that takes the vehicle from an edge and drives it into the center of the patch. And then when it reaches the center of the patch, it will trigger a water sample. So that's something that we do here pretty typically. And then in addition to that, I guess you mentioned communication. So yes, the vehicle surface periodically to surface with shore, but those type of applications, especially if you want to stay with a certain part of a water mass, meaning let's say because everything is moving in the ocean constantly, right? You've got currents carrying these microorganisms, and if you lose that patch of water, then in order to go up to the surface and communicate well, when you come back down, you might be looking at a whole different community. And so those type of applications really lend themselves well to multi-vehicle constellations. And so that's been another focus here, is this multi-vehicle type of operations. And so in the example that we just discussed, you'll have one vehicle that is doing this gradient climbing and looking for a maxima. And then once it finds the highest concentration of chlorophyll or whatever it is it's looking for, it kind of just parks it underwater and stays with that water mass and drifts. And the issue with that is, after a while, you're not going to know what the vehicle is. You're not going to know what type of information it's looking at. And so a second vehicle will typically track this type of sampling vehicle acoustically.
Oh, that's smart.
And then
so one is at the surface looking down, and the other one is drifting with this algae mass.
Well, so that's one way to do it, and we also use autonomous surface vessels in order to track underwater assets. But we typically also have a second underwater vehicle that's profiling around it and tracking it. It's surfacing periodically, and it can relay information from the diving vehicle, and also it gives the scientists more contextual data, because usually the sampling vehicle is kind of parked at one little part of the water column, and in order to get the full contextual data of what's going on, you also need a second vehicle in order to survey and get
the bird's eye view. So one is in the forest and one is at the trees, kind of thing.
Exactly. And so multi-vehicle applications have been a main theme here. And I guess that kind of leads us toward maybe talking a little bit about the sim. Because...
One sec, just before we go to that, what do these vehicles look like? So specifically talking about these surface monitoring ones where we're looking at algae.
Right.
What do the robots look like?
Yeah, so typically they're kind of torpedo-shaped vehicles. That's the most efficient way. And the vehicles that I work with specifically are kind of small size, so they're probably 2 to 2.5 meters long, depending on the type of payload that they have. And the diameter is about 12 inches. And they basically look like torpedoes. I can show you a picture here, maybe.
Sure. Yeah, and I'd love to talk a little bit about how they work and then get into the sim stuff, because the sim stuff is very interesting, for sure.
So this is a picture of one of our vehicles. Those are Tethys-class long-range AUVs. Like I mentioned, these are upper water column vehicles. They're pressure rated for about 300 meters. And what's special about them is really their endurance. We designed
looks like a big fire extinguisher to me.
Pretty much, yeah. If you've ever seen a picture of a torpedo, then it looks pretty much like that. With a mast on top, and that's our communication antenna. Yeah, so I'll go ahead and stop sharing it. But so that's the long-range UV. Now, I guess, like I mentioned, MBARI's really been on the forefront of development of these platforms. And so that vehicle that I just showed, the Tethys-class long-range UV, has been developed at MBARI from scratch. And it's also manufactured here and operated here. And so everything about that vehicle was designed here in-house. These vehicles are special. They're special in their capacity they're high endurance vehicles, meaning they can cover about 1,500 kilometers and stay at sea for, I'd say, up to 2 to 3 weeks, which is unusual for vehicles of that size, and especially for ones that have propeller and they're able to thrust on their own. There are other types of vehicles that don't have thrusters and have longer endurance. But this vehicle is very special and unique in its capacity to, stay out there.
So does it do any? Basically you have a battery in it, and that battery will last for 2 to 3 weeks, and
Correct.
that dictates how long you can do it. It doesn't do any power generation or like go up to the surface and have solar panels fold out or something like that.
But it does. I mean, the power management system is very
Efficient.
Efficient, yes. Every aspect of that vehicle's design is really geared toward efficiency, from the shape to the tail cone and how the hydrodynamic flow and how water passes around it. It's kind of set to minimize drag. And this vehicle specifically is also special because it can change its buoyancy. Meaning most people that put very expensive pieces of equipment in the ocean, they make them buoyant, so if the engine stops working, it will come back up. Well, this one is able to actually change its buoyancy at sea and fly neutral, and that actually gives you a huge efficiency boost because you're not pushing against this upward force. And so then comes the question, okay, if something does go wrong, how do you manage that? And so safety and power management are kind of the heart of this vehicle. And so both have systems that are designed specifically in order to optimize the parameters. The vehicle powers off systems automatically when it doesn't need them, even including actuators. So it's very smart management on board. And when endurance in general is kind of death by 1,000 cuts, right? But if you try to optimize around each parameter, eventually you get a system that is able to persist and be out there for those type of durations. And again, the requirements for those durations come back to the original processes that we've discussed kind of in depth. Pun not intended.
Gotcha. Yeah. So many ocean puns are possible, for sure.
I know.
So with this, when it adjusts its buoyancy, the way it does that is it takes on water, right? Like, so it'll have little cavities or something, and or how does it work?
Yeah, well, actually, our vehicle doesn't take in water. It uses oil. And so it can pass oil into a bladder that's external to the sealed compartment. And by doing that, so if you're taking oil from the sealed compartment and pushing it out to a bladder that can inflate, you're actually changing the volume of the vehicle without changing its mass. And by definition, that makes it more buoyant. And when you want to become less buoyant, you just push the oil back into the sealed compartment, and that deflates the bladder, and the vehicle then becomes less buoyant.
Yes. So the volume changes and the mass stays constant, and that changes the buoyancy of it.
Correct.
Is it a lot of energy to like compress the oil or move it inside to the?
Oil
so
is
I'm imagining like what? It's not.
The oil is it's non-compressible oil.
So it's like some sort of vacuum thing to move it from one spot to another.
Yeah, we have a valve that opens and then a pump that sits inside the sealed compartment and can push oil outside, and it's designed in a way that it can push against pressure even at depth.
Gotcha. That's so cool.
And then
what a clever way of doing it.
There's a lot of also some safety built into there. What happens if suddenly you can't push against the pressure, and so there's some valves that are set to close automatically and make sure that water never makes it back in case of a failure. So like I said, failure management has
one of the big things.
Exactly. Yeah. So pretty much every aspect here. Yeah. Go ahead. Ask.
So you don't want it to fail because you lose your robot. How much does one of these robots actually cost? Like ballpark, if you can reveal that.
Yeah, sure. I guess these vehicles also were designed for what we refer to as end science users. Okay, so if you're a researcher at a lab, you should be able to buy one of these and operate it on your own with a reasonable budget. And so that was kind of the requirements going into that. And so the vehicles, they're actually, not sure if it's a good idea for me to disclose the exact.
Can I take like an order of magnitude? Is it like $50,000 robot platform?
I'd say probably an order of magnitude more.
Wow. Yeah. So it's like ballpark 500,000. So $500,000 almost for one of these.
Yeah.
Gotcha. And that's affordable for large research institutions, I take it?
Well, if you consider what it costs to operate a ship,
I guess
most
it's true.
Most
How
of the
much
ships.
does it cost to do a ship?
Right. So
I guess.
Sorry. Go ahead.
Because it seems expensive, but I have no experience in this, so no real ability to estimate this.
Right. So a big ship, especially one that can operate on ROV, you're probably looking at a few tenths of $1,000 per day.
Wow.
And so if it's a bigger ship, you're around 50 to 60K easy per day of operation. And so, $500,000, I mean, it might sound a lot, but when you think about it in ship days,
relatively cheap.
Exactly. And so that's the idea. And then once you, if you can get the costs in for the vehicle, the operational costs are very, very cheap. You can deploy these vehicles with, a tiny little boat, and then you're stuck with the, whatever communications bill for iridium satellite communication, or your 4G cell. So
they
the
do
operational
4G. So if they're doing like 4G cell service for transferring data, does that mean that you have to stay close to coasts with these, and that's typically how you're using them? Because I would imagine if you're in the middle of the ocean, like very far from shore, you're in the middle of the Pacific, there's no cell towers out there, there's no cell service, but you did mention satellite, so I suppose you could use that.
Yeah, so we refer to those. We have two modes of operation. When you're outside of cell range, we refer to that as over the horizon. When you're within cell range, why not take advantage of cell communication and do big data dumps when you can? I don't know if Iridium is very slow and bandwidth limited, and so
how slow is really slow, like ballpark?
So let's see. Each Iridium packet is 340 bytes, and you get about, I'd say, if you're lucky, 3 to 4 per minute.
Seems
when the vehicle's
incredibly
on the
slow.
surface. Yeah, so
Yeah.
it's tiny, and so we play a lot of games on board the system with compression.
And all sorts of
Yeah,
things.
and also not only compression, but also selecting what
inference?
information to send. What's the most relevant piece of information that needs to be sent? What needs to be sent first versus, if you're only able to get one SBD, one iridium packet out, what is it going to be? And so we work a lot with the scientists in order to understand the use case, get at what is the crucial information that they need for decision making while the vehicle is deployed, and then configure the vehicle appropriately and send it over, and hopefully not spend most of our time sitting on the surface sending packets.
Syncing data. For sure.
Yeah, exactly. So time on the surface is risky for the vehicle because it could get run over. That's probably the biggest risk for these autonomous platforms.
Getting run over, not sharks.
Yeah, right. But also it's time not doing science. So
totally
trying to minimize that. Yeah.
Huh. Okay. So you have these. What long range? What was the next part? Autonomous underwater vehicles, or what was the thing you were saying?
Correct. Yes, it's the long. So these vehicles are long range autonomous underwater vehicles. So LRUVs for short.
LRUVs.
LRAUVs. Yeah.
Doesn't roll off the tongue terribly easy.
It really doesn't. We've had other people try to come up with different, but we're kind of stuck with that one.
Okay. I'm just going to say long-range underwater vehicles. Easier.
Okay.
Okay, so you have these. You were mentioning that you have a bunch of safety precautions on them. Because they're $500,000 platforms. I'm sure that with the cost of a boat, you make the money back, but it's still super expensive. So I think institutions probably wouldn't like to be replacing them because they keep getting lost at sea, literally.
Right.
Can you talk about the safety systems?
Sure. So I guess I'll say that we have 8 of these platforms here at MBARI, and there are others coming up online at Woods Hole and other places where they're building them at the moment. And between the fleet, we have probably nearing 35,000 hours of sea time.
Wow.
And
seems like
so that's a lot. That's a lot.
Can you give me that? Let's see. How many days at sea is that between the 8?
So let's see.
35,000 divided by 24.
Right. Yeah. So let's
divide
like that by
4 years.
4 years worth of. Yeah, it's 4 years of sea time, which isn't crazy. That's a lot.
That's a lot.
And during
have you lost any during this
exactly?
time?
I was gonna go knock on wood, but
question 2.
Right. We've never lost one.
Wow.
And so again, the reason is because MBARI has a lot of experience, and we've basically taken all of our experience and knowledge and built it into the hardware level of these vehicles. So this vehicle has so many safety features built into it in the hardware level, meaning the motherboard itself. If the CPU fries, the motherboard itself has the capacity to turn on the radios
and communicate,
and also fire up a device that drops a weight to make the vehicle positively buoyant.
Oh, stay.
So we have an emergency.
Basically.
Well, no, it will come back to the surface. The drop weight detaches.
Reduces the weight, so it goes up.
Exactly. Yeah.
It's like cutting your weights when you're scuba diving, so that you can start going up.
That's exactly the idea. That's exactly the idea. And then we have transponders and all kinds of other acoustic devices on board the vehicle, and then emergency beacons, so we can always find them. So the vehicle will try as hard as it can to come back to the surface because that's where it can be located. And once it's on the surface, even if the battery is completely depleted, there are secondary radio devices that will communicate with shore and send its position. And so that's one aspect. We also have very sophisticated ground fault detection systems, meaning if there's a cable or something like that that's exposed to ocean water, that can cause corrosion. Just because the electricity starts interacting with different parts like the hull. And so we have a very strict monitoring system for that. We also have, in general, you want the system to be reliable and fault tolerant. so you can continue to do operations. If the vehicle has to surface every 10 minutes because it encountered an issue that it can't resolve on its own, well, operationally, that doesn't scale. And so we have also a health monitoring system on board that's able to power cycle different subsystems and try to change protocols. And so yeah, a lot of thought and effort has gone into making sure that the system will keep doing what it's supposed to do for as long as it can, and only come back to the surface and communicate with shore when it absolutely has to.
Gotcha. Awesome. That's so funny that it power cycles all the things. It's like that tried and true wisdom of just like, if it's not working, just power cycle it. I love that you have the ability to do that kind of remotely with the robot.
Right. Yeah. If it would be a step forward, it would flip RX and TX.
Yeah, I know. Because so just to explain, if anyone didn't get it, it's the transmit and receive wires. So like a lot of times when you're building stuff, you mix up with just the transmitting and receiving, and then you flip it, it works magically.
Right.
So that would be so funny.
Yeah, that's kind of like the classic mistake. But yeah, so with all that, and I guess I also say that we've operated these vehicles now in both Pacific and Atlantic Oceans, and also in the Great Lakes. So they're tried and true vehicles, very persistent, very reliable.
So, and you mentioned you have 8 of them. That's, and between them, they have tons and tons of hours. Is there a plan to like scale it massively and get like 80 of them or 800 of them, or like, so these are all over monitoring everything all at once, or?
Well, yes.
Where do you see this going in the future?
Right, and so I guess we're currently, I think, doing multi-vehicle operations has still a lot of overhead, and so figuring out, I guess, at a first order, how to operate so many vehicles in conjunction, and how to automate some of the processes, ongoing research out in MBARI, and I think in a lot of other places. We've nailed down 2 to 3 fleets of 2 to 3 in doing collaborative multi-vehicle operations at sea with that many vehicles. More than that, you start running into bottlenecks. For example, if they're all using the same acoustic channel to communicate, well, that's kind of like a half-duplex, right? Only one person could talk at any time, and so you get.
Or you say you're like, I'm talking to this one, and then the message, but it's inefficient.
Right, exactly. So we would that's another piece where we have some ongoing research to figure out how we can scale that. But then also the logistics of operating a fleet like that is also, so you have 2 weeks of battery, and you need to, if you have many of those, they really need to be self-sustained and at sea. And
you need some sort of power generation method, probably.
Yes. Correct, and so MBARI has an ongoing project. We have a what we call the energy buoy. It's a buoy that uses energy from waves, and so that charges a battery, and then in conjunction with that.
So is it kind of like it rides along, like maybe say 6 feet down or something, and then there's the buoy moving up and down, creating motion, and then you're using that electrical energy?
This is a whole separate platform that generates power. And then I was going to say, and then in addition to that platform, it also has what we refer to as a docking module. And so the idea is for the vehicles to be able to home back to this device, dock on it, and charge the battery. And we've made some really good progress. So we have a buoy that manufactures energy from waves and stores it. And now we've been we've actually licensed some technology from Northrop Grumman, and they've developed this technology they call Niobicon, which is this metal that's based on niobium is self-healing, so it can coat itself with a very thin layer that doesn't transfer electricity. And so it interacts, when you power it, it interacts with seawater, and it creates this coat around the metal. And so that's kind of like a self-sustained piece of equipment that you could leave in the ocean. And then when the vehicle comes and docks on it, it could expose and just peel off that tiny little thin layer and connect to the power source and charge its battery. And so we've been working very hard to see that through, and we've done some sea trials, and it works. There's still a lot of kinks to iron, but that's
for sure.
Eventually the dream is to be able to have a large number of these vehicles out at sea where they circulate in, come in, charge their battery, do data dumps, and then go back out to sea. And then you can even imagine maybe that wave buoy is something that's mobile, and maybe you can direct that thing and give it a coordinate. Cool. And so I think that type of constellation where you have an energy source in a data sink, where vehicles can come in and charge the battery and do big data offloads and then go back and do tasks, is kind of where we're headed with this, what we refer to as kind of like a mobile observation platform.
And then once you have that, then scaling is a lot easier. It's like maybe the two hardest challenges for this would be the communication part of this, where you're limited in how you can send to multiple ones. And also you're very limited by satellite radio. I wonder if like Starlink or anything will help any of that. That'd be quite cool.
Yes.
Knowing very little about that.
Yeah, there are also other technologies that are coming up that will speed up over the horizon communication. So we're excited to see how those technologies kind of play out.
That'd be super cool. And then the second one would be power generation, because you have to retrieve it after the battery is nearly dead, or around the time that the battery is nearly dead. But if you could somehow charge with these systems or whatever it might be, then you could just stay out and continuously revolve them. And then it's a lot less going out and grabbing it, which I assume is still quite expensive to do, because you need to take a ship, and the ship has to have like a big crane or something to grab it, or whatever it might be.
Sure. And I mean, you don't necessarily, for these vehicles, you don't necessarily have to have a big ship,
smaller.
But if they're far out, I mean, if you're in a coastal environment, that's great. But if it's happening, if you want to do research,
really
further out, or if it's just really far away, then access also becomes an issue. Yeah. And so we're also looking into developing autonomous surface vessels that are able to do deployment and tow outs.
That'd be so cool.
Yeah. So that's another kind of direction that some researchers here are looking at the moment.
And you mentioned earlier that one human operator can work with a few different of these robots that are out. How does that look?
Yeah, so we've put a lot of effort into developing a user interface that's a web-based user interface that allows you to control the fleet and interact with it. And so we basically have a website that gives you all the information you need in order to operate the vehicles, tells you where they are, it shows you on a map, shows you what mission they're running, and you're able to interact and queue up commands and send them to the vehicles through that web interface. Like I said, the vehicles were, really designed with the end user in mind. So when we have big expeditions and experiments out here, the scientists are the ones that are actually running the vehicles and not the engineers. And so we have a training program that we, developed in order to train people to use them with our web interface. And we actually have a number of projects here that are geared toward, improving the user experience and rethinking a little bit how we can do these types of multi-vehicle operations with a single user kind of commanding the fleet. Again, doing 2, 3, 4. That's definitely manageable with a single operator, but more than that, I think it'd be a bit of an overload. A lot of that ends up being, what we're identifying the bottleneck is the ability to predict what is going to happen next, how the schedule is going to work together, how missions. So basically, look into the future and understand what are the next few steps that the fleet is going to do. Currently, it's easy to understand what's happening at the moment, but it's a little harder to understand, how things are going to evolve. And so that's another piece where we're trying to add in, models, or maybe a way to extrapolate out into the near future at least, and give the operator an idea of what the fleet's going to be doing, and not only when it's doing at the moment. So,
gotcha. Awesome. It's very interesting. It's cool. It's cool to imagine scaling this. I don't know. It's really neat to me to have an operator controlling these at a high level and making the plans, and it's neat to consider how that interface might be and how it'll change over time as you increase the efficiency for an operator. Very cool.
Yeah. And I guess, because of the timescales we're talking about for these vehicles, for their deployments, I mean, that's weeks potentially. Doing
Hmm.
development on these systems is very difficult because once they go to sea, there's a lot of overhead. Everything's very slow. And
Yep.
so faster than real-time simulation really plays
Yep.
heavily into what we do.
Yes.
And so I feel like, I think that having those capabilities also, especially in the fleet context, are going to be monumental into developing those abilities to also not
Mm.
only do the multi-vehicle operations at sea, but also how to control them.
Gotcha.
So,
Yeah. Tell me a bit about the simulation.
right. This project is something that we've drummed up a couple years ago. The idea was, we talked a lot about multi vehicles and how difficult at sea operations are and risky. And so the idea was to develop a development environment for these vehicles that will allow us to test um, in the closest way to the conditions that we experience out at sea, um, you know, the challenges and the bottlenecks for these type of operations. And so we had a simulator that was built in that we developed for the system, but we felt like it was time for a facelift. So it wasn't really. I mean, it's a command line tool, so it didn't
Yeah.
really scale well to the multi-vehicle
Uh,
scenario. And so we looked at a few options of what it would take to upgrade it. And eventually we came up with this idea of maybe we should, bring in an external platform, and we started looking around. And that's when we came across Gazebo and Ignition. And we also
mhm.
had some folks from Open Robotics come here and visit and start forming these relationships. And so from here to there, we decided to launch this project to build a multi-vehicle underwater simulation environment for LRUV in Gazebo and Ignition. And
Mhm.
we got funded through the Institute in order to do exactly that. And we partnered with Open Robotics and really contracted the engineering time to do the development for this purpose. And so it's been a fun ride working with the team here at Open Robotics. You know, we weren't really sure how it was going to work out. We absolutely had to have the framework work with the flight code of the vehicles themselves.
Mm.
Typically, Ignition is geared more toward applications that use ROS, where our vehicles run such tiny embedded systems that at the time it wasn't really possible to even get ROS loaded on it. The integration with our software was key, and so we focused on that. And then the second biggest requirement was the fast and real-time capability. And so we also
Mhm.
had concerns with that. And that was part of the reasons why also we went to Ignition over Gazebo Classic, is the runtime is much quicker and you can change different aspects of the system to expedite the runtimes. And so we started with integration, built a vehicle model for LREV, which is now available to download at Fuel. And we can incorporate the links maybe at the bottom here when we're done.
Yeah.
And we slowly started building the pieces and the different plugins that were required. A big piece that we recently completed was kind of like custom sensor environmental data. So your ability to take detailed information from very sophisticated models that model circulation and temperatures and all the different ocean parameters, as well
Mm.
as the biological activity that relates to those conditions, and inject those into the system and have the vehicles operate within that environment that not only has the water properties and waves and wind and all those things, but also has kind of like scientific sensor data that the vehicle would encounter as if it's in the field. And so
Mm.
that's a really nice aspect of the system that I feel we've done a little bit different from the way things are more traditionally done, where you have kind of like an analytical model that describes how properties change using some function. Another piece that we incorporated was an acoustic model. And
Mm.
so vehicles can communicate acoustically in the simulated environment in order to do these multi-vehicle operations. Like I mentioned before, acoustics and coordination is a big piece. And so we have that modeled with the kind of like a standardized interface that allows the different vehicles to send tracking messages between each other and also data. And so that's modeled. And so all the different, obviously the vehicle model is very detailed. So the vehicle has, we talked a little bit about the variable buoyancy system that we have on board, and so that posed some modeling challenges because that's unusual, especially in a simulation environment like Gazebo, for something to change its buoyancy in that way. And so we had to build some infrastructure into Ignition itself, and also come up with the right plugins in order to support that type of performance for the vehicles. And it's pretty cool. It works very well. We're able to achieve fast and real-time runtimes of about 100x factor of real time, which is fantastic. Great. Yes, and so even with a few vehicles in the simulation, you're still at 60 to 80x. So 24 hours of simulation translated into 24 minutes of runtime in the simulator, which is great. And it's something that it's a useful simulator.
For sure.
And so that's been really good. We're still working on now adding. There's a whole another part of the vehicle sensing capabilities that we haven't really touched on that has to do with how the vehicles navigate underwater. And so we're now more focusing on those aspects. And so we currently have the ability to simulate the type of experience that we've described earlier, where vehicles, are searching around for different ocean properties and doing water samples and all that stuff. But now, okay, what about navigation? That's another use case that could benefit a lot from this type of simulation. And so we've worked to add bathymetry using levels, actually. So depending on the position of the vehicle in the simulation, it can load a chunk of seafloor. And so that makes it pretty scalable. And you can imagine tiling huge regions and have them loaded dynamically and in a memory efficient way. So that's,
so you only look at what you need, or only load in what you need at the time, and then it moves over to the next tile and you load that tile in, this kind of thing. Or you load a few tiles around where it is so that it never sees the edge of the tiles. Okay.
Yeah, we ran into that. So the tiles actually overlap. So that's working great. And now we're working on some more acoustic sensors that have to do with sensing the bottom. So they're what's called Doppler velocity loggers. Those are used for navigation. It can tell you how fast the vehicle is flying over the bottom, and then it becomes a question of odometry, keeping track of integrating those velocities into position. And so you're able to use those sensors for navigation. And so that's kind of the next big use case that we're aiming the sim at. Is bottom-aided navigation, what we refer to. And we have some cool use cases here at MBARI. There's a lab that's focused on doing terrain relative navigation that I think a lot of folks have heard of in the context of the lander in Mars, where they use terrain relative navigation to localize and understand where they are before they landed. And so we do the same using the seafloor, using maps that were acquired with the really big, much more expensive vehicles. Later you can load those in and use that in order to localize yourself based on the bathymetry and where you are, kind of like in a SLAM sense. And so so that's another aspect. I guess one more cool piece in that is that together with the simulation plugins and all the pieces that the folks at Open Robotics have been working very hard and doing a tremendous job doing, those are all going to be open sourced, and they already are. And so that's going to be available for the community to use and leverage. And we're hoping that folks pick pieces up, and use them and improve them. So pull requests are welcome. I guess that's kind of like the mantra in the open source community. But in addition to that, we're also going to be releasing a Docker image that has a version of the vehicle's flight code, so folks can play around with both and operate the vehicles with the flight code in the loop. And in addition to that, we also have an interface to the vehicle that's a network-based interface. And so the idea is for folks that can't have access, for example, to the flight code, they're still able to send commands using this interface to the vehicle and drive it from their application. And so we refer to that as the backseat driver. And so the idea will be eventually that you're able, with those Docker images, to create your own application that's able to get telemetry data from the main vehicle application, feed it into your app for processing, whatever your use case is, and issue commands back to the vehicle to, pilot within the environment. And in theory, if we do things right, you should be able to take that backseat application that you've developed and put it on a Jetson or whatever that's mounted on board LRUV inside the hull and have it pilot the vehicle at sea. And so,
that's awesome.
So the idea is very much for this whole package to kind of be something that's deployable by a single user, so they can do development again for their backseat application or whatever using this interface that we've come up with, and later take the same application, put it on board, and have it work at sea.
That seems awesome. I like that, and it sounds like so I haven't been very involved in this at all at Open Robotics, so just hearing about it is very cool. But it sounds like you guys have done a tremendous amount of work to make it so that you have a realistic ocean environment for your simulation, for your robot in simulation to drive around and interact with. So very awesome.
Yeah. We, there's always room for improvement. We really focus on building, I wouldn't say it's the best ocean model, right? There are definitely ways to do things better, and we hope that over time things will improve. But I think the goal was to kind of close the loop to get you to an environment that is close enough to the real thing that allows you to work on, I'd say, kind of guidance level parts, right? So not so much the control, but maybe a layer above.
What you wanted to do.
Right,
sure.
exactly. And debug and work in a multi-vehicle setting. And so, like I said, per use case, I'm sure that we'll continue to improve the system. But at this point, it's pretty good. It's good enough to definitely be able to test out some of these scenarios. And the much faster and real-time capability is a godsend.
Really nice.
I
imagine.
Yeah. So that's really cool.
So thinking forward, where do you imagine this whole project and kind of the work you're doing at MBARI going? So maybe like 5 years, 10 years in the future. Where do you think it will be, or what do you hope it will be?
Yeah. So I guess we're still at the point. So the way I think of it here is that we've done a tremendous job getting a persistent platform that's reliable. And it's taken us, the project for LREV has been running since 2008, so even before I've reached the Institute. But it's taken a while to get to the point where the system is now stable and very, very reliable. And so now, I guess, sensing and planning are the two big next, challenges that we have. Okay, so everything we do on the system is still pretty rudimentary. So we have really cool planning algorithms that climb gradients, but they use pretty rudimentary math. There's a lot more that we can do.
Keep improving.
Exactly.
You're like, keep getting more algae. Like if you keep seeing more, it's good, and if you don't, it's you've reached the center or something.
Right. So the algorithms that we're using are, I guess, there's room for improvement. They're great. Don't get me wrong. We do tremendous things with them, but there's so that's one piece where the autonomy piece where the vehicles can now plan and do things in conjunction together is, I think, where we'll see big advancements. I'm hoping that the system that we described earlier, where we have kind of like a
powered system,
observatory, is something that will come into reality. And I think the sim is also going to be paramount in developing those type of systems because, like I mentioned, there are lots of challenges in communication and other aspects that currently we just aren't sure how we're going to solve. And and being able to simulate everything in much faster real time, it kind of lends itself to iterative methods and other techniques that will hopefully help resolve and close some of these gaps without having to go to sea every time and the overhead that comes with that. And so, yeah, I think this mobile observatory, if we can be there in 10 years, I think that's going to be pretty amazing.
That'd be so cool.
Yeah, and then I guess another piece where I'm really hoping to see this project evolve into is, we've put tremendous effort into building the infrastructure that's, making its way into upstream, into Gazebo and Ignition, into the core of it. And so I think, what I would really like to see is Ignition being adopted widely by the marine community and other folks coming in and using this. At MBARI, we're sure 100% that we can make good use of this technology and this application. But we're really hoping that others also pick it up and use it and contribute back to it and fork it or whatever it is you want.
Yeah.
But use it. We're also lucky in the capacity that we have access to the ocean, but there could be some brilliant minds out there that may not have that type of budget or just straight up, don't have access to the ocean. And so we're hoping that will increase in exposure. People will be able to develop these type of applications and perhaps even communicate with us, and we can get them on the vehicles to run at sea. So that's also a very exciting aspect of this project that I'd like to see evolve, and curious to see what kind of collaborations and partnerships we form with this sim kind of being as the platform that connects,
because it's out in the community. So yeah,
Exactly.
You get a bunch of people that can try it out and start to get involved and see if they fit well and if they really would want to do this. That seems wonderful.
Yeah, hopefully so. And but there are also, other institutes that, already are doing this type of work. There's very little overlap, even within MBARI, different platforms, different code bases. And so there's a lot that we could do for standardization and bringing, putting out different parts of the software, even just interfaces to make things, a little more interchangeable. And if I work very hard developing a terrain relative navigation system, I'm hoping that somebody else can pick it up and use it as well.
Totally.
So that's another piece.
Yeah, it seems like this is the way things go typically when it's a space that's more exploratory. Like, there are very few people or few organizations doing work like you guys are doing. Therefore, there's very little standardization around it. But I think creating the sim is a wonderful thing, because now a bunch of people can try it and they can run their code on your platforms in the simulation. And then there can start to be more buy-in from the community around this and more investment in ways of doing things, which leads to standardization. So I am optimistic for the future and kind of seeing where this will go. I think that will be awesome.
Yeah, hopefully.
Do you, so what advice do you have for people that are, say like a college student or something that would like to be involved in this line of work? What advice for them do you have?
Well, so I was very much in that, position when I first started here. Like I mentioned, I started as an intern here at MBARI, and I actually don't have a formal engineering background. My background is in marine science. So, I think you just have to want it and be curious, and then seek out, be outspoken, don't wait for the opportunity to come to you. So a quick story that, at the time when I did my internship, there wasn't budget for me to come here and be an intern. And I already had met with the PI, and we had discussed a potential project, and I was very excited for the opportunity. But then suddenly there wasn't enough budget to host me. And so that was the point where I was like, okay, I'm going to make this happen. And I reached out and wrote some blogs and ended up raising enough money to be able to fund my own internship. Right. So, but I guess the piece is beyond the money. It's being proactive and really wanting to take part. I think also intellectually, we'd like to see more people from different disciplines, especially more kind of engineering based and computer science based, and come to do ocean research, because there's a lot of room for that type of knowledge to make it into our community and contribute. So if you're looking to be very impactful and help understand what the environment is doing and how we're impacting the environment and how it's changing, this is a really good field for you to come in and apply your expertise or your research or just develop your interests and contribute. And so internships are a great way to start. But a lot of the people that work in this community, because they believe, they want to see progress. They're very friendly and they're happy to help. So get on a website, poke around, send an email. It's always great to hear from people, and if we can help, we try to. So yeah, I guess being proactive and not being deterred. There's all kinds of reasons why not to do things, but if you are curious, just go ahead and shoot out a note or learn something new and push forward. Eventually you get there. I don't know. Maybe that's a really broad piece of advice, but that's what I got.
It sounds wonderful. Lastly, do you have any contact info or links or anything you'd like to make sure that we share with this episode?
Sure. So I guess obviously our simulation framework that we're developing, which is already open and out there, and so we'll include the links. That's actually an OSRF repo or OSRC these days, and we'll go ahead and share that. My information can be found on the MBARI website, and I'll share that as well. I'm also on LinkedIn, Twitter, all those great platforms. So feel free to reach out if you're interested. Especially if you want to use the sim or if you have an idea for a backseat application that you'd like to see running at sea on our Tethys class long-range UVs. Let's talk. Yeah, that's pretty much it. MBARI has a wonderful website that's full with data and interesting stories, so feel free to visit there. But that's pretty much it.
Okay, awesome. It's been wonderful talking to you.
Thank you very much for having me.
Bye, everyone.
Thank you for listening to this conversation with Ben Raana. Thank you again to our founding sponsor, Open Robotics. See you next time.